Oh, I'm out of here.
I love how they have the ripcord button in case you can't handle being recorded.
Yeah, I know. I've never had somebody leave because of that. Well, I will we'll probably have a few more people filtering in, but I'm going to go ahead and start and welcome everybody to the Robert Ferguson Observatory Speaker Series. My name is Stephanie DeRomelar, and I'm the Executive Director of the Observatory. And we're so thrilled and honored to have Eliot Gillum from LaserSETI join us. I'm really looking forward to his talk and hearing more about the SETI Institute and all the exciting things that they do. And I'll introduce him in a second. But before we start, just wanted to remind everybody to please keep yourselves muted. I know there's some people that still are unmuted, so I'll go ahead and do that. But if you can do it yourself, that would be helpful to minimize that background noise. And then we will open up for questions at the end. So if you have questions as Eliot's speaking, just go ahead and put them in the chat. And then I will read those off to him when he's finished. You're also, sorry, lost my train of thought. So real quick about the Robert Ferguson Observatory, for those who are not familiar with us, the observatory is run by the Valley of the Moon Observatory Association, which is a 501(c) nonprofit comprised of volunteer, amateur, and professional astronomers. And RFO has fulfilled its mission of offering educational programs about science and astronomy for students, the public, and in support of educators for about 25 years now. The observatory is almost all volunteer run and typically serves about 9,000 visitors annually, which is very nice. This year, we're about on track of having that again after 2 years where that was certainly not the case. The observatory is located in beautiful Sugarloaf Ridge State Park and houses a 40-inch reflector telescope, which is the largest telescope in Northern California that's accessible to the public, a robotic 20-inch research-grade CCD telescope, and an 8-inch 2-meter-long refractor telescope. We've kept the presentations in our speaker series free to the public to align with our mission of offering educational-based astronomy programs to our community. That being said, if anyone is so inspired to donate to the Robert Ferguson Observatory to ensure that we can continue fulfilling that mission, you can do so on our website, which is rfo.org. Also, just wanted to give a quick little plug for our volunteer program for anybody who's interested or might have a friend or family member or whatnot who is interested in becoming a docent for us or a volunteer for us. We will be doing our next new volunteer training in starting in July. So if anyone's interested, they can fill out an application on our website. So like I said, Eliot Gillum is joining us today from the SETI Institute, and Eliot Gillum is the principal investigator for the LaserSETI project homed at the SETI Institute. His childhood love of astronomy was rekindled at Cornell, where he received a degree in computer science during an elective course on astronomy, in which Frank Drake gave a guest lecture. Further inspired by an alumni talk from Joe Tarter a few years later, Eliot started what would become the LaserSETI project in 2015 after a 15-year career at Microsoft. Today, he runs the project out of his home office and workshop in San Francisco, supported by Dr. Tarter and many other talented and dedicated individuals. So without further ado, Eliot, I will pass it on to you.
All right. Hi, everyone. Welcome to my home office. Let me do the screen sharing thing. And I assume everyone's seeing the presentation now? Okay.
Yes, we can see it.
So let's see, make sure I can change the slides. There we go. I thought I would break the talk into some SETI theory, particularly on optical SETI, since many people are probably a little more familiar with radio SETI, and then get into the specifics of LaserSETI. I'm going to try to cover a lot of material pretty quickly. So I apologize for going fast and not going into some depth that I might like to, or hopefully you might like me to, but I want to leave time for questions at the end. So bear with me on that. Also, I want to say that it's been a while since I've given a public talk. I think there's been like a pandemic or something. And so the slide deck is pretty new, as well as I haven't given this presentation before yet, so bear with me on that as well, please. So hopefully everyone knows at least about SETI, that it is looking for evidence or the lack thereof of other civilizations. Generally, what is meant by SETI is looking for signals, of which beacons and interception are two kinds. Something that was pretty popular in the science press a couple of years ago was Boyajan star, and the idea of structures around other stars that could be observed at great distance, because that star was demonstrating some really odd behavior. And that's generally referred to as SETA, or search for extraterrestrial artifacts. Another cool but non-SETI activity is astrobiology, and that's really kind of blurred into SETI as modern telescopes are starting to be able to image and even do spectroscopy on other stars. We can now start to look for evidence of biology and even potentially technology, depending on the type of molecule we're looking for. But in the interest of a communication SETI, the thing that I think most people think the most about is how would we send a giant message into space? And optical is great because you can focus it literally 1,000,000 times better than radio. And if you take our largest laser and shine it into our largest mirror, you can outshine the sun by 4 orders of magnitude, and that's independent of distance. So clearly, civilizations are quite capable of creating signals that are easily viewed at great distance. However, knowing how to receive such a signal is not the same as being able to send such a signal. If you send a signal from 1,000 light years away with such a system, the beam would only expand to be about the size of the orbit of Mars, which is quite small considering the incredible distance from like 1,000 light years away. But you need to aim that beam. And since space is big, it takes a long time for that beam to travel. At 1,000 light years, it would take 1,000 years to get there. So you have to know where your target will be in 1,000 years. And that problem gets worse as you get further away. So in the short time, it's not so hard. As a relevant example, when we measure the orbits of asteroids, we can now predict where the asteroid is going to be generally out to about 100 years in the future. But beyond that, there's all sorts of chaotic effects, and it becomes very difficult. And something a lot of people don't know is that the stars actually mix. We tend to think of it as this big swirling thing, and it seems like this nice regular pattern. But there's actually a 3-dimensional structure. The stars are mixing on about a 10,000 year time scale, swapping positions, which one's closer to another. And so as you get further out, it becomes much more difficult to figure out where a star is going to be by the time your signal gets there. One way around this, however, is to have basically an inconceivably bright signal that if you're illuminating whole galaxies from other galaxies with something that is, using the output of a star converted into a laser, things like that, then you don't have to aim so much because you can just kind of paint the sky. But that's not a great logical out from the difficulty in the aiming problem. So people wonder if maybe we could just sort of hear other civilizations communicating. And someone has studied this, and the real problem here is that space is really pretty empty. And so the conclusion was that unless the beams were unreasonably wide, given any sort of density of civilizations, that the interception was not a realistic scenario. Very cool, NASA is trying to develop, or continuing, I should say, to develop communication technology to allow us to downlink more data from our spacecraft. But fortunately for them and unfortunately for SETI, it doesn't take much power to generate a lot of bandwidth to be able to communicate between something as far away as the moon, say. And the other problem is you generally have a body behind those things generating and receiving the signals. So any overspill doesn't go anywhere, it just splashes on the Earth around it. One very cool scenario, however, some project called Breakthrough Starshot was announced for a couple of years ago. And their idea is they want to actually send a spacecraft to Alpha Centauri, and they want to get it there within 1 generation. So their goal is to accelerate a 1 gram, 1 square meter light sail with chip and laser and everything on the spacecraft is 1 gram, using 10 million 10 kilowatt lasers to 20% of the speed of light, so that the spacecraft could get there in only 20 years. The acceleration from this is obviously pretty inconceivable. But the thing that's really cool about this is that it's something that we're doing for ourselves. It's not somebody trying to reach out and do considering the presence of another civilization. It's just something that we want to do to explore another star system. It might be something if you wanted to send, people or a more complex spacecraft, and you wanted to get there in any reasonable time. This is basically one of 2 ways that you can get to any fraction of the speed of light. The other is antimatter annihilation. So there's some really interesting properties besides the fact that it requires fewer assumptions about what they're trying to do. One, the little eye chart here is that it sweeps across the sky. And so it actually really spends a measurable amount of time illuminating us as it tracks the spacecraft that's accelerating. The other thing is, even though this picture shows the laser either being absorbed or bouncing back directly towards the Earth, neither of which is realistic or good, in reality, you need to keep the spacecraft in that beam. And so you actually need to shape the beam so that it's stronger on the outside. And in fact, you want overspill illuminating all outside the spacecraft, because you don't want any part of the spacecraft not illuminated. And you want to make sure that as it's not perfectly stable inside the beam, that it wants to stay in the center of the beam, versus if it slips out, then that part's not being accelerated and it's going to instantly pop out of your beam and there goes your spacecraft. So that overspill means that you're going to be illuminating the whole part of the sky behind the track between your laser and your spacecraft as it's going off on its orbit. One last point would be that once you've built this 100 gigawatt laser and you're launching these 1 gram spacecraft, you're not going to want to use it just once. You're probably going to want to go to multiple stars or send multiple craft. And so there's a repetition sort of implied by an investment like this. Turns out nature also gives good ways to make lasers. The carbon dioxide in Mars's atmosphere is actually excited by the sun and radiates at 10 microns. That's about the same temperature as body heat, but if you put 2 mirrors in orbit around Mars, you could basically capture that solar pumped laser and use it to send a signal out. This is kind of a lesser known cousin of the stellar maser, which radiates in radio frequencies. Another scenario people might have heard of and thought of is gravitational lenses, which is extremely cool in that you can focus sort of a huge amount. Then that gives you what we call aperture or gain in astronomy. The problem with these is that they're a little bit logistically challenging. The focal point for the sun starts at 542 AU, which is really far out there. Certainly makes Pluto look like a planet. And then the time it takes to go around the sun at that distance is over 12,000 years. And so it's definitely a great idea. I feel confident we're going to do this as a civilization probably in the next 100 years for being able to quote a friend of mine, read license plates at 1,000 light years away. But it's also very logistically challenging. And then kind of a meta scenario that I think is important is to remain open-minded, that as much as we can conceive of all these ideas, we don't know what else might be conceived of, because we really have no idea how different another civilization might be. And so in general, having fewer assumptions is better, I think, in terms of how you approach SETI. The more you imagine the other species has decided X and Y and Z, I think the less likely that would be, since we know nothing essentially about them. So in summary, the interception scenarios are not really possible, but the beamed energy propulsion one is one that I think LaserSETI and in general SETI is a great target for SETI's surveys. Somebody intentionally trying to signal or using a gravitational lens, certainly that would be easier to get our attention. With LaserSETI, the Martian laser, that's way out in the far infrared, and so that's not one that any current SETI project I'm aware of could detect, but it's at least conceivable. And then it's also pretty hard to assess what we don't know. So second half of the SETI theory, there's a whole bunch of factors I won't go into, but I did want to touch on a few. One, why do we look for narrowband sources? And the basic answer there is because nature doesn't produce them. SETI is very cool because we kind of say, okay, well, we think we understand nature and all these different things that it does. And so anything outside this envelope must either be new nature or another civilization. And one thing that our civilization does for good physics reasons is produce narrowband signals, both in the optical and the radio. And so looking for those seems like a great way to, one, throw out all the nature we think we understand, and two, hopefully identify another civilization. Two commonalities between radio and SETI, however, is that it's terribly important that your source images to a point, because otherwise it's lens flare, and that's not what we're looking for, because it means it's a local source. And one of the ways we do this is by having a long baseline, either with interferometry or co-observing, that I'll talk about with LaserSETI. So there's been a number of very cool optical SETI surveys in the past. Here's some parameters from a few of my favorites. But the thing I want to highlight with this slide is the field of view of these surveys was quite small. The sun or the moon is about 1/2 degree across, which means it's about 1/5 of a square degree. And that, since the sky is over 41,000 square degrees, there's a whole lot of suns or moons to paper over the whole sky. And as you compare that to the numbers in the table, clearly they weren't covering a lot of sky at a time because they had a narrow field of view. And so what they chose to do was to only spend a certain amount of time on each target, which is great if what you're looking for is there all the time, like nature. But if what you're looking for is transient, then if you look for 1 minute out of a year, then there's a whole lot more minutes out of the year that you're not looking, and you could easily miss something. The other thing is, as you think about stars, since a lot of these target stars, there's a lot of them, with hundreds of billions in the Milky Way. And even if you just narrow it down to the 1,000 light years closest to us, there's 18 million stars. And that actually turns out to be the size of that yellow dot relative to the size of the Milky Way. And so even no one has covered 18 million stars with a targeted survey yet. And that's just a tiny fraction of our neighborhood called the Milky Way. This slide is really not meant to be read so much as understood as having confidence in what you find in your SETI survey is difficult. And if you look at the history of pretty much every SETI survey ever, it either hasn't found anything, or it found a bunch of maybes, a bunch of things that like looked weird. It popped up one time. We went back and studied it a bunch of times and we never saw it again. The most famous of that is the wow signal. And if you contrast that with Sagan's correct observation that extraordinary claims require extraordinary evidence, then I think it's clear that SETI surveys need to think very carefully about not just finding something that goes bump in the night, but proving that you really did find it and it's really there, and it's not just some other signal that confused you, or some electron bouncing around your instrument that you didn't expect. And as a measurement of this, in radio SETI, the SETI Institute has an instrument called the Allen Telescope Array in Northern California, much more northern than us, Northern California. And in a 6-year observation program, they found 300 million signals, many of which required follow-up in order to get down to one signal that was interesting enough to merit a human studying it and also figuring out that it was noise. And so what I think is very cool about this is it's effectively a measurement of how much noise there is out there, even on an instrument designed to do SETI, that you have to filter through. It also sort of helps explain why when you're using a telescope and you're taking pictures and you're stacking images and throwing away little blips here and there, you're probably not throwing away a SETI signal. Those are probably just noise. And in order to accomplish this task of finding the needle in the haystack, we're going to have to find things that are 1 in a billion, 1 in a trillion, even more. That's just how many signals there are out there. So moving along to what are those wonky white boxes on top of the observatory? You can see them if you're a little bit further away. They're on the back side of the roof, so you have to go up the hill, or maybe be a good 100, 200 feet away from the front of the observatory before you can see them. And that is not LaserSETI's satellite dish, that's the internet connection, but it does look cool. Before I move on, I want to acknowledge the team, because this is definitely a team effort. We have a bunch of people that volunteer on the project. I particularly like to highlight in this context Dan Kinnan, because he lives up in Sonoma County and has been taking care of some of the maintenance and other sorts of operational tasks there. So you may see him at the observatory, and I'm very grateful for not having to drive from San Francisco every time that something needs to happen at Ferguson. But as you can see, it really takes a village of people working on the project, smart people both within the SETI Institute and outside the SETI Institute, to advise and make this thing go. So I don't want to get too deep into all of this, but in order to achieve the original goal of LaserSETI, which was all sky, all the time coverage, you need to have that field of view, but you also want the time on the sky if you're looking for infrequent signals. I already talked about why we care about lasers and high confidence. The other thing that's been really critical in LaserSETI is being cost effective, because if you design something that costs millions and millions of dollars, then it's a lot harder to build a lot of them and put them all around the world. And so looking at what was realistic, both in terms of funding and engineering in order to do good science, was really a part of the design from day one. And that, for instance, includes the fact that while we can do a limited characterization of a signal we find, we're really designed to just find the signal. There's obviously a lot we don't know about, what's the modulation on the signal, what's the repetition, what's the wavelength, what part of the sky. We're really designed to prove that there's something there. We really did see it, but we may not be able to, if they send the prime numbers, once a second, then that'll be easy to decode. But if they're beaming us the Encyclopedia Galactica at 1 gigahertz, then that's not something that we're set up to be able to analyze. Also, if we're looking for things that are transient, we want to run for a long time so that we have a chance of catching it once, or ideally even 2 or 3 times. Spectroscopy I'll talk about in a second. The false positives is pretty interesting though, in terms of confidence. When we first designed the instrument, the goal was to have no more than 1 false positive every 1,000 years at the global system rate of 13 petapixels per day, peta being 1,000,000 billion pixels. And so the design actually worked out to more like 1 false positive every 30,000 years, and we don't actually have the whole system online. So it's fair to say that we can have very high confidence in whatever LaserSETI finds, and we actually need to redo that analysis now that we've got a lot more data. So the 2 basic science concepts involved in the LaserSETI instrument are spectroscopy, of which Pink Floyd had a great appreciation, and this crazy CCD readout technique. Normally, when you take a picture, you open the shutter and expose all the pixels, and you close the shutter and you read out all the pictures, and you have a picture. With time delay and integration, I don't have the time to get into it because it's fairly hard to explain, but basically we're shifting and smearing things out vertically. There's a good reason for doing that, and it works, but it's complicated to explain, and unfortunately we just don't have time here. But the spectroscopy is kind of our secret weapon for being able to sort photons by their color so that we can group them and understand, are they spread out? Because pretty much everything in the sky is a broadband emitter. Stars emit at almost every color of light. And satellites, for instance, reflect the sun. And so even though it may look like a white flash, or it may even have a color, it's still a very broadband signal because it's reflecting the sun. But using this transmission grating, we can distinguish a narrowband single color pulse because it will only be 1 color, which means that it's only 1 point in the spectrum versus stars. And what this allows us to do is, since traditionally in optical SETI, they're looking at photon arrival time as the only way to determine what are special photons from all the trillions and trillions of normal photons. But since we can sort the photons by color, then we can not only look for pulses that last a nanosecond, but it expands our range of signals we can discover by a factor of 1 billion into pulses that could last seconds or maybe even a minute. And that's important if you remember the eye chart earlier on, where some pulses from the beamed energy propulsion can last tens of milliseconds or even seconds. So let's see if I can make this play. So what does it look like to look through the instrument? Here you can see all of those stars with the point source and then the blobs on either side, which is the spectrum. If this were a color CCD, then you would see the rainbow there, but it's not, so it just looks like a white blob. You can see the clouds there. If you're quick, you saw a plane come in the bottom. And so this at least gives you kind of hopefully a frame of reference for what it looks like to see what the instrument sees. The caveat here being that these are registration frames that we take every 15 minutes. All the other outside of those 10 seconds, the rest of the time we're in that TDI mode, which is smearing things out. But this is at least sort of conceptually what the camera is looking at. Just to show you what events look like on the camera, here's some false positives. That you can see the plane in the bottom right as it streaks across with its anti-collision lights and strobe lights flashing. But there's actually, even if you leave the shutters closed and just read out the CCD, there's a lot of particles flying around out there. And since we have a very sensitive camera, you see all sorts of arbitrary little dots and squiggles and things happening there. The one in the top center is the closest to what we're looking for, but if you look at that one, you can kind of see that there's a lot more light on one side and than the other, and that helps us know that it wasn't really the same event, because if it were the same event, it would have been split 50-50, and you'd see it balanced on either side. Just to describe how we go about sorting this computationally, because we obviously can't do this manually. The first thing we do is to look for just, is there anything in these pixels worth computing on? And that's just an optimizer, because we don't have enough computational time to do the analysis on every single pixel. So then we look, is the thing that we find round, or is it at least vertical, as we're smearing things out vertically? And if that test passed, then we look to see if there's a mate to it that is the right distance apart and is sufficiently similar to be credible as part of the same event. And then we actually have 2 cameras per instrument, because again, that TDI readout, one reads out vertically and one reads out horizontally. And that's how we recover the X and Y coordinates. And then we also look for the same match. We have to find 2 events, one event in each camera, that are compatible in order to consider it a 4th level candidate, which is the output of the SETI detector. So the instrument, you can kind of think it's really just kind of a host for 2 of these cameras. Now you can see those in the gray box in the center, the big blue things. And logically, they're fairly simple, with just the transmission grating in front of a lens in front of a camera. The other boxes I'll explain in a second. But since we have such a wide field of view, we don't have to track anything. We just let the sky drift over us overhead. And I just explained the TDI part about why we have the 2 cameras and one reads out in each direction. And basically that gives us good time sensitivity, which if you think you might see a brief signal, it's very important not to have a traditional exposure in astrophotography would be 15 or 30 seconds. And if you're looking for a 1 millisecond event in a 30-second exposure, obviously you've got a lot of other things going on there that could make it harder to find. So what's in the box is a number of off-the-shelf components, an Intel NUC i7, like a lot of people have in their laptop. Really, this is kind of a laptop computer in desktop form, nice and small. The Raspberry Pi is kind of the central nervous system that reads all our data and executes actions. The fancy numbers on the camera is really just to say that it's got a really big sensor, which gives us our wide field of view. And the quantum efficiency is very high because we want to be very sensitive. Lastly, all the components, everything holding everything together is all custom 3D printed in polycarbonate. And then the enclosure itself is medical grade stainless steel in order to be super strong and not degrade in the elements stuck outside for a long time. So once you have this instrument, you have to put it around the world in such a way as to see the whole sky. And unfortunately, whoever designed the Earth did a really bad job. There's some really big oceans that are hard to cover, which means that we want to be close to the coasts in order to cover the part that is over water. And the South Pacific, as you can kind of see, is really big and hard to cover. And then basically, while we have some overlap and we can't look too much towards the horizon, otherwise we get too much air and moisture interfering with the light that we're trying to see, we end up having a bunch of overlap, which isn't so bad between instruments. And if you notice, particularly in the animation, a lot of the lines line up. And that's because every instrument is paired with at least one other instrument at another site to look at the same patch of sky. And I'll explain more about that in a minute. But so basically with about a dozen sites around the world, each with 4, maybe 5 instruments. The 5th one helps cover the poles because it's hard to look in the right direction from there and cover the poles all the time. But that's how you cover the whole sky. You can see here, there's actually 4 red cones in Northern California, which is imagining that we put 2 more at Ferguson to match with the 2, sorry, that would look east. Right now we've got the 2 at Ferguson looking west to match with the 2 white cones out in Hawaii that you can see. So why do we do the pairing? Well, for a couple of reasons. One, it means not only do we have the 2 cameras that are in one instrument looking at an event, it means we have 4 cameras in 2 instruments looking at an event, which gives us an incredible statistical confidence. But we also have a clock accurate enough to measure the propagation time delay given the long baseline. And so we can do an extra physical validation that the signal really came from outside the local neighborhood. The other reason is that the sun rises and sets at different times, so we can cover that field of view for more time, although we would prefer to have the 2 instruments, always working together. And no site has perfect weather. And so if we have bad weather at one site, then at least we'll have hopefully 1 instrument at the other site. The other thing I want to talk about here is sort of what else is LaserSETI good for? Because it's good at characterizing fast, bright events, then things that burn up in the atmosphere also meet that criteria. And that's why NASA gave us one of their meteor cameras, which is that globe thing on the cylinder near LaserSETI, specifically so that it could cross-calibrate the way they usually look at the sky with the way LaserSETI looks at the sky. And in general, sort of any science that is looking for bright transients, LaserSETI is probably fairly interesting because it has this wide field of view, high time resolution, and spectroscopic capability. So in summary, just to sort of throw some numbers at you, just to create one instrument is 27 days of continuous printing just for all the brackets and components that go into it. That 75-degree field of view is roughly equivalent to 9,000 moons on the sky, but our pixels are small enough at about a 40th, I think it's a 43rd of a degree, that we can spatially resolve a source out to 25 times further than the moon, which is another aspect of confidence if you want to show that the signal you saw not only happened, but happened not locally. Our sensitivity is such that it takes a couple hundred photons in order to detect a signal. And the computing that has to happen is analyzing both cameras, streaming out data at over 100 megabits per second. And that's why we need those i7 computers. We've now had about 2,600 hours of observation on the sky. That results in over 100 terabytes of data in over 8 million files. Those sample events I showed you, we've captured 18 billion of them. And one thing that we haven't talked about publicly at this point, that C4 is the matching events. Well, a double C4 means that you have the matching events in two cameras, and that's what a SETI detection looks like. And we have had 3 of those, but unfortunately, all 3 turned out to be a new kind of camera anomaly where the rows start coming out of the camera flipped horizontally, and it tricks the detector into moving a static source. It teleports it to another part of the field of view and then flips back, and it confuses the detector. So we're filtering those from the data set and talking to the camera manufacturer and try to understand why it does that. We installed the instruments at Ferguson in 2019. And then thanks to the pandemic, it took us an extra year to get the next 2 instruments onto the top of Haleakala and Maui. And then the great news is that we got 3 more observatories that we are funded to build, that we're going to cover probably a good third of the night sky. I haven't done the exact analysis yet, and we'll have to build 10 more instruments, potentially 2 of which will go at Ferguson, in order to fill out that picture I showed you earlier on all sky coverage. So as kind of a point of clarity, I think many people will be familiar with fast radio bursts that were discovered just in the last decade, basically. And these are extremely energetic sources, very bright in the radio sky, that last for a millisecond. They're thought to happen up to about 10,000 times a day. And somehow the first 75 years of radio astronomy missed them. So I think it's very exciting for what LaserSETI might find once we get a chance to analyze all the data. Whether we find SETI or we just find new nature, LaserSETI is, I think, uniquely positioned to find some really cool stuff on the sky. And that, I will move on to a very important slide, thanking the amazing people at Ferguson. This is a picture of the volunteers and victims who happen to be there at one point, but is probably half or even a third of the people that helped that day back in August of 2019. And it was a crazy busy day, and everyone was really helpful on the installation. I'd like to specifically thank the board, Dave, Gordon, Larry, let's see, Elaine has been very helpful. I'm going to forget too many people there, but basically both the administration of the observatory as well as the docents that I've encountered have all been just wonderful. And I'd also like to point out that it's just a great site. It's beautiful. It's got a great view of the sky. The facilities there are pretty unmatched for a very long distance around. And so I think I'd like to express my gratitude for Ferguson and just emphasize what a gem it is that we have here. So I'll shut up and just say that we built this new website recently that's got science, it's got papers, it's got talks, it's got links to other projects, it's got live views from the cameras. The sun is still up, so you'll see the sunset at Ferguson through the little cameras, the little black boxes that you can kind of see there. That's the daylight camera that we use to check on the physical instrument. And you can see what we're doing. Sometimes when we pop the cover off, you'll see us working on it. You can see the science data, well, not the science data, but those registration pictures and what the instrument is seeing basically in real time. And you can stay connected with us on your favorite social medias, so you don't even have to remember to go to the website, but please do.
Thank you so much, Eliot. I know you had a lot to cover in a short amount of time, so that is a challenge, but that was perfect. We did have a few questions. So the first question was, beam shaping of the Breakthrough Starshot program is something I hadn't heard of. That's really cool. How would you do the beam shaping?
How do you implement the beam shaping, or what's the goal of it?
No, how do you implement?
That is beyond me in the physics. I can find you some papers. At least one, maybe 2 of the talks at Breakthrough discuss their annual SETI-ish conference has been on this topic. You do at least have the freedom of, you've got these 10 million lasers and how you aim them, but how you phase up the lasers, I'm not quite sure how much of the beam shaping problem is mechanical versus interferometric to produce that shape. I haven't actually seen anyone talk about how you would execute it, only about how you would shape the light sail and what are beam patterns that you would want to have.
Well, we don't have the 10 gigawatts worth of laser yet, so we've got some time. They've got some time to figure it out.
Yeah. Yeah. Thankfully, we don't need Dr. Evil just yet.
And then the second question, also from Dave, have you considered crowdsourcing examination of any signal you might find?
You know, yes and no. There are other analyses I'd be interested to do first. You know, a naive classifier looking to group events by similarity, just to sort of break the data set into things that look similar. And that would, I think, be the most interesting next step. The classifier that runs right now is specifically designed to detect the SETI signals that the instrument was designed for. So I think the first thing beyond that is just looking for, well, what sort of buckets do things fall into? And then let's try to break down those buckets. I think crowdsourcing is a great idea. I think Tabby Boyajian, you know, has proven for a lot of people how valuable crowdsourcing can be, because they're the ones who found that star. But it does require a lot of effort, and we have a lot of data. And so figuring out what we would actually hand out to people would be a project in itself.
And that skinny satellite link on our roof is a limiting factor too, isn't it?
Well, no. So we sneaker net the data out of Ferguson. So we from Hawaii, we're streaming it continuously, and it's a bit of a struggle to keep up because the instrument produces data pretty fast. But we keep a disk array at Ferguson, and each instrument has its own disk that fills up. It's a circular buffer basically, and then we copy that off every night onto the disk array if it's there at Ferguson, and then we bring it to the data center, we plug it in and copy the data off and get it back to Ferguson and start the process over again. So that 117 terabytes is just about every pixel of data we've recorded since first light back in August of 2019.
Impressive.
That's more than half of the storage we have. And I never really planned to store all of the data. It wouldn't be that bad if we wanted, you know, so it's a 200 and something terabyte array for, I think it was $8,000. So it, you know, if we wanted another quarter petabyte, you know, that's only $8,000. That's really not that bad. It's kind of inconceivable for those of us who've been in the computer industry for, you know, more than a decade or two. So we could decide to have more of it. But as we bring more instruments online, then unless Google or Microsoft or Amazon decides that they want to give us some unreasonable amount of storage, then we will exhaust whatever reasonable amount of storage that we can afford.
Great. And then John asked, do you still use the Drake equation? And if so, what is your current estimate?
Yeah, so we don't really sort of, speaking generally for SETI Institute scientists, we don't, let's see, I had a slide here, don't really spend a lot of time trying to calculate it. It was actually formulated by Frank as just a way of setting an agenda for the first SETI meeting back in, I don't know, 61, 63, something like that, someone might know, to kind of break down the problem. It is also a really cool way of estimating things, and we have learned a lot about how many planets there are and how much life might be out there. We still don't really know anything about intelligence, and that's actually kind of the point of this slide, is I really consider SETI to be in a race with astrobiology. I think it's very difficult to argue without invoking a higher power that there isn't other biological life out there. There's too many places, we see all the molecules, there's too much time. The idea that it could, you know, you could get a cell once is basically statistically impossible according to the evidence we have now. But intelligence is another thing. There's more than one intelligence on Earth, but only one of them has any significant technology. And we are in a real-time experiment to see how long that technology can last before it blows itself up. And so we really don't know anything from a science perspective about intelligence. And there's some really great work going on in communication with dolphins and whales and studying the intelligence of octopi and that sort of stuff. But the telescopes are and robotic probes within the solar systems are, you know, doing some really cool science. We're finding a lot about, you know, water on Mars. We're looking at sending some cool probes to other interesting places in the solar system. As I said earlier, telescopes are starting to characterize exoplanet atmospheres. And so, you know, I wouldn't be surprised if we have an answer to the astrobiology question in no less than 20 years or so. TESS has a chance already today, right now. And there's a lot of other ways we could make the discovery with astrobiology. SETI is just a lot harder to predict. So it's the hare in the tortoise race. But the tortoise is actually moving pretty fast, which is amazing. You know, with the stuff we've learned about the universe in the last 2 decades, it just makes astronomy such a great science these days.
Absolutely. Somebody asked, and I'm assuming they meant RFO, what was the name of the Northern California Observatory you mentioned, which I assume is the Robert Ferguson Observatory, but I don't think you mentioned another one in Northern California. Did you? Okay.
Yeah, no, that's it.
Okay. And we are in Sonoma County, and the address is Kenwood, on top of Sugarloaf Ridge State Park. Somebody asked.
The park is awesome too, I have to say. My kids love it there.
Yes, definitely. And then somebody asked if you could put up the website information again. I think someone else answered that though. It's laserseti.net is the URL. And then Merrick asked, is there an analogous color brand to the RF SETI quote water hole?
No, not really. You have two competing phenomenon. One is that the higher energy, the photon, the shorter its wavelength, the more narrowly it can be focused. So for a given aperture, the bluer it is, the more narrowly you can focus the beam. On the other end of the spectrum, you have the dust in the interstellar medium, which happens to be of the size of the order of visible photons. I mean, obviously it has a distribution, but there's a lot that is that sized. And so what you have is, as you go into the infrared, you get a lot less extinction from the interstellar medium at great distances. But at the same time, that's also a pretty limited range. I think actually, here, I have a slide on this. So if you go far enough out, there's just a bunch of dust. So at 30,000 light years here, 33,000, sorry, kiloparsecs, you're looking at less than 1% of all the light making it through. In this middle range, you have where the blue can make it through, or sorry, the red can make it through, but the blue gets, you know, down, you're at 98% extinction or so at 10,000 light years. But then as you get in towards 3,000 and 1,000 light years, you're losing, you know, maybe half, but it's not that big of a deal. So for getting through, you know, long distances, infrared is better, but it's not a whole lot better in the sense that by the time you get far enough out, you're still just losing almost everything. So that's really kind of it. I mean, I would, you have to think about what their, is this a beacon that they're trying to send? Do they want it to be seen by us? Is it designed for us? In which case it might be green in order to get through our atmosphere better. Is it related to how easily they can produce photons of a particular wavelength? Are they doing it for a starshot type program where they care about just a specific range of focus And they frankly would for a StarSat type thing, you want bluer photons because one, you care about how far you can focus it because that means a longer acceleration phase, which means a lower power requirement. Two, as the craft starts to go relativistic, those photons start to Doppler shift to the red and do less good as they hit your light sail. So if you're doing that, then you probably lean more towards the blue. So there's no real hard thing there. You kind of have to pick what context you're in before you know a little bit more about how much you care about these different things.
Great questions, everybody. Were there any other questions? And you can either put it in the chat. Feel free to unmute yourself as well.
Yeah,
I was just going to say, I think when someone asked about the Northern Observatory, I think he was talking about the Allen array. You were talking about the radio array up north.
Yeah, that's the Allen Telescope Array. That's up near just north of Lassen National Forest. I don't know what else you want me to say about that, but it's a great place to visit. It's a beautiful area, and you can actually visit the array itself. They have a visitor center, and it's a great team up there working on that telescope.
Well, I think that was all the questions. Eliot, thank you very, very much for your time. Really appreciate it. And it's it was really nice hearing more about everything and what you do and the science behind it. So thank you very much, everybody, and have a lovely rest of your evening. And hopefully we can get you on here another time and explain more of what you do.
Yeah, hopefully we'll even have some in-person events, and
yes.
Rather than me sitting and talking for half an hour, I love just answering questions and talking with people about stuff. It's really, SETI it's exploration, and it's great to explore science, and it's great for people to explore their questions.
Absolutely. Well, thank you. Thank you very much, everybody. Thank you for your time, and thank you to Eliot especially. And hopefully we will see you all at the observatory soon.
Great presentation. Thank you, Eliot.
Thank you.
Thank you all.
Thank you, guys.
Thank you. Bye-bye.